page 1. Okay, so what are some of our objectives today? And again, like I said, to cover these objectives, we need to get some background material in. So we'll go ahead and get that material in on the board. We want to develop an understanding for the concept of resistance. And last time we talked about resistance. Anyone remembers what we said resistance was? Resistance is the property of a material to do what? To resist what? Resist. Correct. Resist electrons flowing through it, or to resist charge from flowing through it, right? Also, we want to verify the validity of Ohm's Law. So Ohm's Law is really not a law, but it's something we observe. And we're going to look at Ohm's Law, what it is, and why it's true. So the emphasis of our experiment is to have a circuit where we're going to change the voltage that goes to that circuit, and we're going to have a fixed resistance, and we're going to measure the current. So by measuring the current, we're going to see there's a pattern that as we change voltage, current is also going to change when we have a fixed resistance, and that would be Ohm's Law. Also, we want to use Ohm's Law to determine the resistance of a resistor. Knowing some information about the resistor, for example, if we know the voltage across the resistor and we know the resistance of that resistor, we can use Ohm's Law to determine the so we know the current flowing through it, we can use Ohm's Law to determine the resistance. We also want to verify the relationship between current and voltage for constant resistance, and we want to verify the relationship between linear resistance and the slope. So in other words, we're going to take our data we get from this lab and we want to plot our data, all right, to see what kind of distribution we have. So the equipment we're using the power supply, also a breadboard, connecting wires, digital multimeter, and a number of different resistors. Okay, so again, this is sort of a review of resistance, but we'll just go a little more in depth. All right. So again, and last time, if you remember, I just put a few facts on the board about resistance. Last time, what did we say resistance? What did we say about resistance? Okay, we said resistance is when a material has a property where it resists the flow of electrons through it, right? And so today we will be learning that some of the ways we can visualize what is happening in the material that it resists the flow of charge. One way is that electrons collide with atoms. So as the electrons flow through a material, the electrons will collide with atoms in a material, and that restricts movement of electrons through it. Now, again, most times when we talk about conductors, we're talking about material that is crystalline in nature, except if we're talking about liquids, like water. But when we talk about metals, most metals have a crystalline structure. And what do we mean by crystalline structure? We'll have the atoms connected. Okay, most times we have, say if we have like metallic bonds here. Just imagine this with me. So the crystalline structure means that we have some sort of pattern that is repeating. So we have the atoms and they are connected to each other, right? Using metallic bonds, and we have sort of like a crystal pattern like this, where the pattern is repeating through the material. So we can sort of connect them like this. So imagine that all of these dots here are the atoms, right? These are the atoms. See, let's use the example of copper. These are atoms of copper, right? And they are held together with metallic bonds. So again, what is happening is that they are sharing electrons. So we have an atom of copper here, okay, and we have a number of bonds here, right? All through the material. So in other words, there is space in between what we're saying is that there is space in between these atoms, right, for the electrons to flow. Because what happens here when when an atom loses an electron, we said it becomes an ion, right? That electron actually can jump from atom to atom. So it can jump from atom to atom, or it can move through the material. Right? It can move through the crystalline material. And in most cases that's what we have happening. Okay, sometimes because electrons, when they leave the atom, they cannot travel very far because they have limited energy. So they can travel, say for example, this one travels for a little bit, and again, what happens, it loses energy. So when it loses energy, it goes and it joins another atom, right? Until it gets energy, and that phenomenon happens all across the material. So again, when we say electrons are moving through the material, we are not meaning that one electron is entering a piece of wire here. So again, if you look at a piece of wire, one electron, I'll just put the negative here, one electron doesn't enter a piece of wire and go all the way through to the end and come out here. This doesn't happen. Okay, the energy, when an electron becomes a free electron, it only has a limited amount of energy. And that energy only allows it to travel so far. So after a while, what happens? It loses the energy. Again, we said energy cannot be created or destroyed. So again, this energy that the atom has, right? It has energy here, and that energy becomes so high that it now has enough force to break away from the parent. So now that energy is put into motion. It's converted now into what do you call that? Kinetic energy. So the electron is moving, and what happens as it moves? Right? As it moves, it loses energy. Correct? So that energy now is converted into kinetic energy. As it moves, it loses energy, and when it loses energy, then it's almost like reabsorbed into another atom. Why? Because there is attraction. Okay, it falls into another atom here, right? And again, that process happens not only here, but randomly all through the material. Okay, so again, we said in a piece of wire, we don't have one electron going all the way here. What happens? This one enters the wire here, and it joins here. We have another one leaving and joins here, and so forth. And that happens all through the material. That is why when we connect a circuit and we flip the lights on, we don't have a delay before the lights come on. Immediately what happens? Immediately we have electrons from the end of the wire. Electrons are leaving the wire and coming out. So as soon as we turn on the switch, we have electricity immediately because the electrons start flowing immediately. Alright? So again, for resistance, we say one source of resistance is that the electrons, they collide with atoms in the crystalline material. So that's one source where our electron is coming from. So we say that moving electrons collide with atoms. In the material. Okay, and now we're using only one electron here to show our example. But imagine when we have this hooked up to a source, right? We have a certain amount of current. For example, we hook it up to a power supply. Just imagine we have millions of electrons flowing through this material, right? Of course, we're going to have some collisions. Yes, we're saying that they will lose energy and they will be absorbed by the other atoms and so forth, but we also will have collisions, which adds to our resistance. Again, we said that, last time we said that resistance converts electrical energy into what? Someone remembers? So a resistor is a device that's manufactured to have a particular value of resistance. So we said the unit of resistance is the ohm, right? So we said that resistors, they have a function. What do? They convert energy into, someone said it last time. Correct. So yes, resistors. So I'll put here resistors. So resistors convert electrical energy into heat. And again, we said Energy cannot be created or destroyed, right? We said when the electron is moving, okay, that is current, because we said the amount of electrons that move, the amount of charge we get in 1 second is actually the current that we have, right? So the fact that the electron is moving, that is a form of energy, right? That is kinetic energy right there. When the electric energy, so what the resistor does is that it actually slows down the motion. Okay, so that energy that the electrons had, they were moving with that energy. Because of the resistor now, this kinetic energy now is converted into heat. In other words, it's absorbed from the electrons. That's why we said resistors, we use resistors to limit the amount of current. So in other words, they limit the rate of flow of charge. And again, we use the example of a pipe. We said if we had a lot of pressure coming in, say we connected to a grounding water system here, and the water comes at 40 psi. All right, 40 psi. Okay, so if we open our tap here, we'll get 40 psi. I'm sure right here, we got 40 psi here. Okay, if we wanted to use a resistor, now again, psi here, pressure is almost like our voltage. But if we want really, our current is like our flow. So if we had a large pipe, all right, we'd get a lower psi, but we get a higher flow. All right, now that flow rate is what we're interested in. This is our current. Okay, so if we want to limit the flow rate, we need to get a resistor, right, to make the pipe smaller. Okay, so we can do that by using a smaller pipe, or we can do that using a device that has a smaller output, so that we can resist the flow. And that's what they are. This is what the resistor does. It limits the flow of current. It converts our energy into heat. It says, I'm still in the first paragraph, a material's resistance is directly proportional to a couple things. So again, we said resistors are made to have a particular resistance. But then we can look at materials as a whole, and we can determine based on the shape, the length, the size, and the type of element they're made from, we can determine their resistance. So if you look at it, it says, a material's resistance is directly proportional on its length, it is inversely proportional to its cross-sectional area, and the resistance of a particular material can be calculated as R is equal to rho L over A. Again, think this. Let's look at what this equation is telling us. R. Can everyone see the board? Yes?
Yes, sir.
Okay. So R is equal to L over A. Now this coefficient here is a coefficient of resistivity for a particular material. So for example, copper is going to have a particular coefficient of resistance. Alright? So to determine the resistance of a piece of material, we need to know what type of material it is. And based on the type of material, we'll get the coefficient of resistivity. And then we need to know, well, what length of material do we have? And what is the area of that material? Now let's think. And also you can think in terms of a pipe. Say if we have the same material, we have the same type of material. Say we have copper. Alright, and we have a pipe. We have a solid piece of copper wire. Okay, that is in a cylindrical shape. Solid piece of copper wire in a cylindrical shape. And we have two pieces of wires. And they have two different diameters. Okay, as you can see. And this is L here. So again, if we look at the equation, it tells us that to find the resistance is the coefficient of resistivity times the length over the area. And we say that the length is directly proportional to resistance. What do we mean by that? We mean if the length increases, what happens to the resistance? Let's look again. If the length increases, what happens to the resistance? Because we have resistivity times length. So if the length increases, the resistance of the material increases, right? And think of a water hose. The longer the hose, the more resistance it's going to have to water flowing through it. The shorter the hose, the less resistance. Alright, so we're saying same thing for a conductor, conducting electrical current, and we talk about resistance. The longer the conductor, the more resistance it will have. And we're saying here that area is inversely proportional. What do we mean? The larger the area, the smaller the resistance. The smaller the area, the cross-sectional area that is, the smaller the area, the larger the resistance. So if you look in our equation here, A is at the bottom. So we say it's inversely proportional to resistance. Okay, I might need a charger. Okay, so as we so again, if you look at our conductor here, think of a water hose. If we have this big hose here, okay, why doesn't when the fireman comes to out a fire, he brings a small hose like this? What do you think? Do you think that the fireman is interested in pressure or is interested in volume of water? Well, both, right? But he wants a lot of water to out that fire in a short space of time. So he doesn't bring a small hose from loose. He has a large hose, right? That can take a lot of water, right? Think of the conductor is the same way, same principles. The smaller the wire, right? The smaller the wire, and that small wire, it says that we have a very small cross-sectional area, right? Okay, that will tend to a higher resistance. Then the larger the wire, okay, larger the wire, more current will flow. So if we have a lot of flow of current, it means we have a small resistance. Now when we talk in terms of length, the longer the wire, the more resistance, the shorter the wire, the less resistance. Any questions about that? Anyone has an Android charger?
Oh, come on, man, Doc. You gotta upgrade, man.
Yes.
Gotta get out.
Thank you, thank you. You guys need to get with it. Hey?
You said the smaller the wire, the bigger the area?
No, no, no. Think that when we talk about wire, it's cross-sectional area. So large wires have a larger cross-sectional area. Smaller wires will have a smaller cross-sectional area.
And as the length increases,
As the length increases, resistance increases.
okay.
Thank you for the charger, Nagua. So as length increases, resistance increases. So just look at the equation. Right? This equation tells us if we increase L, R is going to increase. If we increase A, right, the bigger the denominator, it means the smaller the total value is, right? Okay. Okay, let's move on. Okay, so again we said each material has a specific coefficient of resistivity. Okay, what we want to talk about now is the temperature coefficient of resistivity. With each material, right, and again, the smaller the coefficient of resistivity, the less resistance the material has. So for example, materials that are good conductors like silver, gold, copper, aluminum, these materials have a low coefficient of resistivity, correct? Materials with a high coefficient of resistivity, something like carbon and other materials, okay, these are not very good conductors. In fact, carbon is not a very good conductor, but what we do is that we take carbon and we add it to a material. So the more, so for example, we can make our own resistor. We take a material, right, and we have conductive elements and we have resistive elements. And based on the ratio of conductive to resistive elements, we can determine the resistance of our resistor. For example, most of the resistors we use in the lab are carbon resistors. They have a percentage of carbon inside. So the higher the resistance, the more carbon will be inside, because carbon has a higher coefficient of resistivity. Again, the other thing we'll talk about is temperature coefficient of resistivity. And what does that mean? Temperature coefficient of resistivity. In other words, it tells us how temperature affects this coefficient here. Again, we said conductors have a low coefficient of resistivity, right? And resistors or insulators would have a higher coefficient of resistivity, because this is directly proportional to resistance. But we're saying with temperature coefficient of resistivity, we want to know how temperature affects this. Now there are two things we need to know. Some materials have a positive temperature coefficient of resistivity, and others have a negative temperature coefficient. So let's look at the first one. What is positive temperature coefficient? Okay, what this says is that if the temperature increases, okay, this is what it is. When temperature increases, if T increases, what happens to resistance? Resistance will increase or decrease? What do we think?
Increase.
Positive temperature coefficient. It says if temperature increases, resistance
Increase.
increases. Okay, and this is critical to know because in some cases, anytime your circuit is heating up, guess what will happen? You'll have more resistance, and so you try to avoid heat, right? You want to avoid heat in your circuits. You don't want things to overheat. Overheating is never good. And then we have the negative temperature coefficient. What do you think what happens in this case? Okay, in this case, as temperature increases, what happens to resistance?
Increase.
Incorrect. Resistance will decrease.
Decrease.
So again, with positive, as temperature increases, resistance increases, and again, vice versa. As temperature decreases, resistance decreases. With the negative, as temperature increases, resistance decreases. Okay? So again, we said copper has positive temperature coefficient. What are some materials with negative temperature coefficient? These would be your semiconductors like silicon, etc. Okay? So again, we want to talk about the different types of resistors. And so I have a box passing around with different types of resistors. We have some that are heavy duty, some that are light duty. And of course, you saw those we use for the lab were very small. Okay, what's my paper? This one, huh? No? Okay, let's look at page 3. It says, so we said we have two types of resistors. We have variable and we have fixed resistors. Okay, a variable resistor is designed so we can change the resistance. So if you notice in the box, we have this type of resistor. And it has a handle on it so we can actually adjust it. So again, if you look here, this is the variable resistor. We can actually turn this one here to adjust the resistance from 0. So this one says 500 ohms. So we can actually turn this here and we can actually adjust the resistance from 0 to 500 ohms. This will be called a variable resistor or potentiometer. Now the symbol for this, right, is going to be this one right here. So on top of C on your handout, you can write potentiometer.
On C?
C. Okay, on page 3, on C, you can write potentiometer. Okay? Potentiometer.
Oh, it's right there. Never mind.
Okay, it's in the figure if you can spell it. It's a potentiometer. Now this one is a variable resistor, but it has 3 legs. Okay? What it has a fixed resistor, which is 500 ohms, and then it has a selector. So if you notice in the symbol, you have a fixed you have the symbol for a resistor. Okay? So look up. Okay, can I get your attention please?
Yeah.
So again, for this one here, in the symbol for this potentiometer here, in the symbol, you notice we have a fixed resistor, right? Now, this one says 500 ohms, so the fixed resistance is 500 ohms. And then what we have a selector now, and that selector, when we turn the knob here, we're actually selecting what amount of resistance we want from that fixed resistor. So the fixed resistance is 500 ohms, and with the selector, we can take the selector up and down. So we can go from 0 ohms, which is the bottom of the resistor, to 500 ohms. In other words, this is almost like a shot. So we are selecting which part of the resistor we want to use. Then we have a rheostat, which is the first one, which is a truly variable resistor, a rheostat. And then we have D is the symbol for a fixed resistor. E is the symbol for what?
Shit. Battery?
Battery, correct. And what is A the symbol for?
You say what?
A.
Ground?
Okay, A is the symbol for ground. Most times, our negative terminal, we'll use it as ground because our voltage will be with respect to ground. Alright? We have one negative terminal and one positive terminal. And the difference between them would be 5 volts. So most times we set the negative to ground, to 0, and we use the positive at 5 volts.
What was B? Rheostat?
B is the rheostat. If you look on the figure diagram, all of them are listed in order, correct?
Oh.
Oh, okay, yeah.
Okay. Okay, again, so we said, if you look in the box, we have different types of resistors. They can look different ways. Someone tell me, before we go forward further, why do we have some resistors being smaller and some being larger? For example, you saw that some of them look like they were gold coated, right? Why are some small and why are some large?
Different size currents.
Different size current? I mean, you're partially right, but that's not the answer I'm looking for. Why do we have different size resistors? Why do we have different size transformers? Right? Sometimes we have transformers in our homes, right? But then we see the electricity company have a transformer on the pole, and it's very huge. Why do we have different size components most times? Go ahead.
The larger it is, the more it resists.
Resist? Not really. Because the large one, for example, the large one and the small one have the same resistance value, but they have something that is different. Okay, the answer is that it's the larger one is able to dissipate more heat. We said resistors convert energy into what? Energy into heat. So the larger one can dissipate more heat. So we say that it can dissipate, it can handle more power. Now we'll define what power is and you'll see why. So the larger one can dissipate more heat. Okay, so let's define power before we move on. We have power and everything is rated in watts, right? Because watt is the unit for power. But what really is power? And of course the guys who love the cars will talk about the horsepower, right?
Yeah.
Okay, so what is power? What do you think? What is the difference between a 1 horsepower car and a 200 horsepower engine? Faster? Okay, you want to talk? Okay, so this is power. Power is the measurement. Power is the rate of using energy. The rate of using energy. Okay? Anytime you hear rate, what comes in your mind? Time. Okay, rate. Alright, just like current is the rate of charge per, right? Rate of charge. Power is the rate of energy. So essentially, the equation is going to look like this. P is equal to, I can put here work or energy over time, where work is in joules and time is in seconds. Okay? So again, power is in watts. So 1 watt is equal to 1 joules per second, right? So if I use 1 joule in 1 second, okay, this is 1 watt. Again, think of it. We're not talking about how much energy energy they use. We are talking about the rate at which they use energy. Again, look at this example. If I have 1,000 joules of energy, okay, I gave Miss Oates 1,000 joules, and I gave my brother here 1,000 joules. Okay, and he decides that he's going to use his she uses hers in 10 seconds, and he uses his in 1 second. Which one of them use the most power? His, right? Because it's the highest rate of using the electricity. Right, so again, if we have, we said the resistors are bigger because they can dissipate more heat. Again, we said the resistors convert energy into heat. So the bigger one, right, will be able to convert energy into heat, right, faster or more than the smaller one. So it can dissipate more heat than, and again, most times for components we use ratings. Right, we see that it's rated for a higher power than this one. For example, the one that we use in our lab, this resistor right here, this resistor is rated for 1/4 of a watt. 1/4 of a watt. Alright? But some of those that you have in the box that I gave you, some of them have 10 watts on them. For example, this one says it's rated for 50 watts. So it can dissipate a lot of heat. Alright? This one says it's rated for 10 watts. Okay, so compared to this one, these guys can dissipate a lot of power. That's why they're so bulky and big. Because they can dissipate the heat and they're not going to be destroyed. This one is just going to burn up. It's just going to smoke up, it's going to crack, and that's the end of it. But this one, based on the way they're constructed, they can take a lot of heat, they can dissipate that heat, but the resistance can be the same as the small one. So let's keep that in mind. Okay, so now I want to come to resistor color codes. Alright, we said the resistors are manufactured to have a certain resistance. In the case of the big resistance, they are written on them. For example, and this one says 10 watts, 100 ohms, and 5%. So all the information you need to know is on there already. It tells you the wattage, tells you the resistance, and tells you what is the tolerance of the resistor. So we're going to talk about tolerance now. Again, but most of the small resistors we're using, all right, in this lab we're going to use the small ones, right? And it says we can determine the resistance of these components using the resistor color code. Anyone heard that before? No? Okay, so again, instead, for example, these ones have no writing on them. So you cannot read this one and say, well, what it is. And it's not very efficient to measure it each time, okay? You don't want to have a meter to measure it. But there's a code that we can use to actually determine the value of the resistance. Okay. It says the value of the resistance, the nominal value. It says resistor color codes are color bands placed on carbon resistors that can be used to determine their resistance. The first band is the first digit. The second band is the second digit. The third band represents the multiplier. The fourth band is used to state the tolerance of the resistor. And what is tolerance? Tolerance tells us how accurate the resistor is. And how do we use the tolerance? It tells us what percentage of the resistance we should expect. And we'll do an example. All right? For example, if I have a resistor in my hands with some colors on it. Now I want you to turn to the back. If you look on the back, I placed the resistor color code there for you. Alright. Everyone see page 11? Okay, so we have the resistor color codes there. Okay, so the resistor I have in my hand, the first digit is orange. So I'm going to write it. We have orange, and we have orange, and we have brown, and then we have gold. What does that mean? What does orange mean? What is orange? What digit is orange represented? 3. Okay, so we have 3 again. What does brown represent? 1. Okay. And what does gold represent? 5%. Again, the fourth band is the tolerance. So gold represents 5%, or plus or minus 5%. Okay. So again, using the resistor color codes, so please pay attention. Using the resistor color codes, alright, we have the first number represents the first digit. So again, these bands tell us what? They tell us the resistance of the resistor, right? Approximately what it should be. So the first one tells us the first digit, so I'm going to write the resistance here. So the first digit is 3. The second digit is also 3. And the third band tells us the multiplier. In other words, it tells us the number of zeros we need to add to that number. So based on this, how many zeros should we add to this number? 1 0, right? And then the last one tells us, so right now we have 330 ohms, and we are told that the tolerance of this component is 5%, plus or minus 5%. And again, tolerance the manufacturer is telling you how accurate the manufacturing process is. They're saying, hey, this resistor is 330 ohms, but based on our processes, if you measure the resistance, it can be 5% greater than 330, or it can be 5% less than 330. So what is the range, based on the tolerance, what range can this be in? Again, look, I'm going to do the calculation for tolerance. Please pay attention, you'll have to do this yourself. Okay, so based on this being 5%, the actual range for the resistance is going to be 95. So again, 100 minus 5% is 95%. So it's going to be 95%, so 0.95 times 330. And so this is on the lower side, and on the upper side it can be 105%, right? 1.05 times 330. What does that come out to be? Someone with your calculator, let's calculate this one first and that one, please. Pardon?
Wait, can you explain that part again?
Okay, so again, tolerance tells us how accurate the manufacturer's process is. Okay. So using the tolerance, we can know when we measure the resistor using our ohm meter, what is the lowest value it can be or the maximum value it can be. Alright?
I got the maximum.
Okay, what was the maximum?
346.5.
And the minimum is
Ohms. Huh?
313.5.
Okay. So again, the tolerance tells us, based on the errors in the manufacturing process, what percentage we can expect the measured value to be. Because, okay, nothing is perfect. No process is perfect. Any component that is manufactured has some error. And so the tolerance is accounting for the error. It's telling us the value can be either 5% above or 5% below. Now again, there are different tolerances. We have 5%, we have 10%, we have 15%, and we can have as accurate as 1% as well.
From 100?
Yes. Okay. Any questions about this? Let's do another example.
I have a question.
Go ahead.
I was confused on how you got the 330.
Okay, let's do another example. Let me get another resistor. Okay, so I have another resistor I picked up here. So the first band on there is brown. What does brown represent?
1.
I'm going to put it right here. We have brown.
1.
Okay. The second column is black. What does black represent?
0.
Okay, the third column is brown. What's brown represent?
1.
Wait. Oh, okay.
The third column, bro?
So it's 101.
No, he's doing different.
Okay, the last one says gold. What tolerance is gold?
5%. Let's get it, man. Professor, I'm paying attention.
Okay, all right. So based on our color codes here, what is this is our resistance. What is the first digit in our resistance?
1.
So 1. What is the second digit?
0.
How many zeros do we have?
1.
So what is the resistance here?
100.
100 ohms. We need to use the unit for resistance, 100 ohms. Okay? So now, based on the tolerance, what is the maximum value and the minimum value we should expect from our resistor? So again, this tells us the nominal resistance, but then when we measure it, we see what it actually is. But we can use the tolerance and guess to know what is the highest it can be, what is the lowest it can be. Again, the highest is going to be, the lowest is going to be 95% times 100 is going to be 95 ohms, correct? 95 ohms, and we're going to have 1.05 times 100 is going to be what? 105 ohms. Okay, does everyone understand this? Yes, no?
Sir.
Okay, let's do one more example. Alright, so here I have a resistor here. The first band is brown. The second band is brown. Someone will have to give me the resistance. The third one is red. Okay? What does brown represent?
1.
What does brown represent?
1.
What does red represent? And the tolerance is red as well. Okay, how much percentage tolerance do you think red represents?
2.
Red represents 2%.
Oh.
Okay, again, red in the fourth band represents 2%. Okay, so what is our final resistance? What is the final resistance?
1100.
Just tell me the whole number.
1,120.
Okay, 1,000 ohms. That's it here. Final.
Oh.
Then the tolerance tells us the highest and lowest. So what is the highest value we can get for in terms of resistance? It's going to be 1.002, right? Times 1,000, and we have 0.95 times 1,000. What are we going to get? Sorry, not 95, but 98. Yes? Anyone calculated yet?
I got 9.
You got 9 what?
988.
Okay. Again, this 1,000 ohm, we can. How else can we write this? How can we write 1,000 ohms using our suffixes, engineering notation? It's going to be how many?
10 to the 5th.
Okay, no, we don't write it like this. We say how many? We normally say that this is 1 what? 1K. 10 to the 3rd, we use the suffix 1 kilo ohm, right? Or 1 kilo ohm. So we can write this as 1 kilo ohms. Yes.
Why wasn't it 1,000?
Yeah, how you gonna
Okay, so again, listen up. What's the first number here?
1.
Okay. What's the second number?
1.
Okay, I have an incorrect here, so this one here.
I know, I said.
Oh yeah, the first time like that. I'm like, man, it's too hard. I'm tripping now.
Someone is throwing me off.
Oh man.
Hey, recalculate these two, please. So this is 1.1K. Okay, so the first number is 1. Second number is 1. The number of zeros is 2. So what is the highest number going to be? Hey, only clean language in this class, please. Clean language.
Oh no, Professor, that wasn't me.
Okay, so
No, I'd say it was you.
That was me, my bad.
Okay. What's the highest one?
1,122.
1122. What's the lowest one?
1,078.
What's it?
1,078.
Okay, make sure you put the units at the back of it. The unit is in ohms. Not ohms. Ohms.
Oh.
So are we gonna be able to use this? Are we gonna remember that?
You can have the stuff. In fact, you can put the app on your phone, but it's better if you remember it. Okay, you can just have a small acronym to remember some of that. At least if you remember some, you're better than some other people, right? For me, I use this acronym. Bad Boy Roy. B Roy. Okay, so just Bad Boy Roy, I have 5 of them already. I don't even know the others, but I know Bad Boy Roy. So I know that this is black, brown,
Red, orange, yellow.
red, orange, yellow. Right? So I know the first 5 and I can survive. Okay, so at least you should have an idea. It's faster than going and measure or going to look it up. Okay, let's move on to the next part. So now we want to talk about Ohm's Law. What is Ohm's Law? And who is Ohm's?
Relationship between voltage across the linear resistance elements.
That's correct. So Ohm's Law is actually an observation that Ohms observed. Alright, so again, Ohm's Law provides a relationship between voltage, current, and resistance. Ohm's Law is an observation. It observes that if the resistance is fixed, current is proportional to voltage, and voltage proportional to current. Okay? Again, if we have a fixed resistance, the voltage across a component is proportional to the current flowing through it. So if the resistance is fixed, so again, note the keywords I'm saying here. If we have a fixed resistance, what kind of resistance we have? What do we mean by a fixed resistance? When we say fixed, it means that it's not changing. For example, when I give you the small resistance here, it's fixed one. You cannot change the value. It doesn't matter what you do. It's a fixed resistor. Alright, so for Ohm's Law, it says if we have a fixed resistance and we decide we want to increase voltage here, we decide we're going to increase voltage. What we'll find out is the current also increases proportionally. So here, let's say if we have 1 volt here, 2 volts, 3 volts, 4 volts. Alright, and say we have a fixed resistance of 1 ohm. 1 ohm. Alright? What we're going to notice is that the current across our component is also going to increase relative of directly proportional to the voltage. Okay? So in this case here, let me show you the equation for Ohm's law, and we will also guess the current. So again, we have current here. So Ohm's law tells us that current is equal to voltage over resistance. Now we can take the same equation and change the subject to find resistance and current. So what would voltage be? Voltage is equal to what? Go ahead. Yes, voltage. If we to get voltage as the subject, we need to make resistance go on this side, correct? So we're going to have current times resistance, I R. And what if we wanted to find resistance? How do we find that? If we want resistance here, we need to divide by current here, right? So what do we have left? V over I. Okay. So Ohm's law just tells us the relationship between voltage, current, and also resistance. Alright? Very simple. If you remember one of them, you can get the others, right? So again. So again, let's look here. Let's look at this equation for now. Just this one right there, the red one here. If we have a resistance of 1 ohm, right? This is our equation here, 1 ohm. Correct? And we are increasing our voltage. So we started with 0. So if we have V of 0, then we have current of 0, correct? Because we said no voltage, no current. Voltage pushes the current. What happens when we go to a voltage of 1 volt here? So again, remember we have 1 ohm here. What happens when we go to 1 volt? What will our current be? 1 ampere. Right? So it's going to be 1 ampere. Okay, remember this is staying fixed. This is fixed, 1 ohm. What happens when we go to 2 volts? According to our equation, if we change to 2 volts, 2 over 1 is what? 2. So our current is going to be 2 amperes. Okay, so again, we have here 1 ampere. Here we're going to have 2 amperes. Again, if we go to 3 volts, our current is going to be 3 amperes. Okay, this is all Ohm's law or Ohm's observation tells us. Okay, so we are saying that if we have a fixed resistance, that the change in voltage is directly proportional to the change in current. So as a result, we expect our result to be, we expect it to fit a straight line. Alright? Now, we can actually take the slope of this line and find our resistance, which is what we want. So we'll be doing some graphing. Alright? Okay, it says an electric current is said to have a resistance of 1 ohm, like we said. An electric current is said to have a resistance of 1 ohm when a voltage of 1 volt causes 1 ampere to flow in a circuit. So how do we know if we have a resistance of 1 ohm? When 1 volt causes 1 ampere of current to flow. This shows that current is inversely proportional to resistance, and resistance is, so as resistance increases, current flow decreases. Again, if resistance element is linear, the resistance is equal to the inverse of the slope of the line. So in other words, we can find resistance by plotting change in voltage over change in current. Again, remember that when we find slope, what is the formula for slope? Formula for slope? Rise over what? Rise over run, correct? Okay. So again, for us to plot voltage, for us to for our slope to be equal to resistance, we need to have voltage on this side, correct? And current on that side. because the rise is going to be voltage and the run is going to be resistance. Okay, so rise over run. So that ends up being, on this side here we have current, so we have now current over voltage. This is the opposite of resistance. What is resistance? Resistance is equal to what? Voltage over current. So how do we get, if we have our plot like this, how do we get our slope to be equal to resistance? We need to take 1 over this one. So in other words, if we take 1 over the slope, so resistance is going to be equal to 1 over this guy. If we take 1 over slope, which is the same thing as 1 over current over voltage, then we end up having this guy here. Voltage over current, which will give us our resistance. So in other words, when we plot our graph today, we are going to plot it in this way. We are going to assume a fixed voltage, and then we are going to get a corresponding current to plot our slope. Alright, but we cannot, so again, we will take this information now to calculate our resistance. Alright, but we cannot do it. We need to take 1 over the slope. After we find slope, we need to take 1 over the slope to find our resistance. If we take 1 over the slope, it's going to give us what is called conductance. Now, conductance is the opposite of resistance. Okay? Okay, so let me tell you about conductance before we go into the experiment. Okay, so again, we say conductance is the opposite of resistance. Okay, and just think of it this way. If we have a voltage source here as a battery, and we have 1 resistor here. So we have a voltage, and we have a current flowing, and we have a resistance here. Alright? Our resistance, we can calculate it as being R is equal to V over I. Alright? So this resistance tells us how much resistance there is to the flow of current. Okay? So again, and you can think of the analogy of a pipe. We have water flowing in the pipe, and we have a valve right here. Okay, so we can so if we have water here, right? And we have an output here. So we can tell 2 things about the valve. We can tell what is the resistance, right? In other words, how much resistance is being put on the flow of water. So we can tell the resistance. And we can also tell the conductance. Well, okay, you told me how much resistance is being put on the flow of water, but conductance tells us, well, how much water is actually passing. Alright, so the two, they talk about the same thing. Resistance tells us the resistance to the flow of electric charge. Conductance is telling us, well, how much charge is actually flowing. Alright, so in other words, here we have resistance and conductance. And we see that they are actually inverse. So resistance tells you the resistance to the flow. Conductance tells us about the flow, how much is actually passing. So here's resistance, and conductance is the opposite. So in other words, when we use G for conductance, conductance is 1 over resistance. Okay, 1 over resistance, and if resistance is V over I, then conductance is also I over V.
That's the G.
Yes.
So G means conductive?
Yes. So again, it's just describing the opposite situation. Resistance describes how stuff is being resisted, and conductance tells us how it's being conducted. Okay, any questions about that? Let's go through the procedure, then we'll go through what steps we'll take in the lab. Okay, procedure number 1, it says use a resistor color code chart on page 11 to determine the nominal value of each resistor on your table, recorded on your table 1. Record the tolerance of this resistor and calculate the smallest and largest resistance. That one is very easy. Alright? Again, table 1 is right here, and on that table you have 3 resistances. Right? You have the nominal resistance here, and then based on the resistor you have, you need to find out what the tolerance is. Whether it's gold, or whether it is 5% or 2%, correct? Then you also need to calculate the maximum resistance and the minimum resistance, and then you will take your meter now and you're going to measure the resistance of the resistor. And if it falls within the range, you're going to check in the box. Alright? Super easy. Let's look at step number 2. Okay, I think we talked about all of this. We're going to jump to step number 4. Are we there? Everyone there? Step number 4. So after we measure, we take our three resistors, we record the tolerance, and we calculate maximum and minimum, and we measure the resistance of that resistor, and we check whether it's in the range of the tolerance. We go jump to step number 4 that says, this test measures skin resistance. Like last time we talked about electricity, we said, based on the skin resistance, it determines how much current enters, right? Enters our body. So we're going to do a couple tests. The first one, we're going to hold the lids of the ohm meter and we're going to measure the resistance, take that down. The second one, we are going to squeeze it and we're going to take that down. And the third one, we're going to moisten the fingers. Okay? I'll give you guys some liquid so you can moisten your fingers, and we're not going to shock ourselves, we're just going to measure the resistance, right? When we moisten our fingers, and we're going to write that down in the lab. Okay? Then after we've done that, we're going to record that in the second table, and we're going to move to step 7 that says construct the circuit in figure 3. Now again, we are not using the Arduino, so instead of using the Arduino, we're going to be using our power supply. Okay, where's figure 3? So in figure 3 here, you have the Arduino, and in this lab, we're using the Arduino for adjustable power supply. Now we're not going to do that because we have an adjustable power supply in front of us today, and so we're not going to use pulse width modulation either. So if you look at our circuit, it's very simple. In fact, it doesn't even have an LED. It only has one power supply here, and it has one resistor. Very easy. Alright? Very simple, very easy, just so we can get the point. What we're going to see is that the voltage across the resistor is going to change proportionally to our voltage. And the resistance is going to remain fixed. So we actually will calculate our current. Okay, so we're going to construct this circuit. So that's the next step. And so after we construct the circuit, let's go over the test procedure. Right? The test procedure is super easy as well. So we'll start with number 8. So again, keep in mind the data we want to gather in this lab is similar to this. So the first step, it says adjust the power supply to 1 volt. So again, we're going to adjust our power supply to 1 volt. We make sure we measure that voltage using our voltmeter. All right, when it's at 1 volt, then what we're going to do, let's move to step 9. Okay, so super easy. We set up our circuit. So let's look at our circuit here. We have our power supply, plus and minus, and we have a simple resistor. All right. So then we have our multimeter, which is going to be a voltmeter, right? So I'll put V here. So this is the positive terminal of the voltmeter, this is the negative terminal. Alright? So what are we doing? First thing, we're going to adjust our voltage to how many volts? To 1 volt. Alright? And then we are going to record whatever voltage we found.
All up in my spaceship. Yes, you should be scared. All up in my spaceship. Yes, you should.
I'm ready. So like we said, first thing we're going to do, if you look in what we need to do, we have 3 resistors here. Now I put these resistors there, but based on the resistors that you receive, you need to put the value of the resistors that you receive. In other words, I have 3 sets of resistors here. 1 set here, and I have this set here and this set here. So you're going to get one of each group is going to get one of each, and then you need to calculate the resistance of that resistor, right, using the color code. So and after you have done that, you're going to put this resistance right here. So for example, I'm going to start with this one. So this is black, brown. Sorry, this is brown, black, brown. And of course we said this was 100 ohms. So again, I'm going to start. Can I have a pen? Can you use your pencil please? So again, first thing I will do, calculate what this is using the color code. Put my 100 ohms here. The tolerance is gold, so this is plus or minus 5%. The maximum resistance is going to be 105. We already calculated this one. The minimum is going to be 95 ohms. all the units here. The measured resistance, this is where I need to measure the resistance. Now I can do this just by turning this to resistance and measuring the resistance. Okay, it comes to 99.6 ohms. So I read this here, 99.6 ohms. And it says, is this within the range? Yes, it is within the range. So I just put a check right here. Now you need to do this not only for this one, but you have this one and you have one of these ones as well. Okay, so let's move on to the second one. Second one, we have 3 sets of data to get. So the first one says with dry hands, we need to get the resistance of the body. Alright, so just touch it lightly. So I have 21.36 mega ohms. So I write that down. 21.36 mega ohms. Then it says I need to squeeze the lids. So I'm going to really squeeze them. And of course, we'll have a lower resistance. 6.41 mega ohms. Big change. 6.41 mega ohms. The last one, I need to moisten my fingers. Now I don't have any liquid yet, but when I moisten it, then the resistance is going to be lower. Okay, so I'll bring a cup of water here so you guys can just moisten your fingers, right? Okay, so the last step now, we're going to go to the circuit. Okay, we said here we're going to use a 470 ohm resistor. Okay, so I have a number of 470 ohm resistors here. If you do not get the 470 ohm, however, you may use any resistor that you choose, alright? So it doesn't really matter as long as we have a consistent value and the resistor is fixed. So here I have a 330 ohm, not a 470. So again, the circuit is very simple. We are told to construct this circuit here. And like we saw on the board, only thing we have is the power supply and the meter. So again here, instead of using the fixed power supply, we're going to be using the adjustable power supply. So negative is here, positive is here. First thing we do is to turn it on. Make sure that the current is up and the voltage is down to 0. So the positive goes to the resistor here. The negative goes on this side to the resistor as well. Alright, and then the meter goes directly across this. In other words, we are just measuring what is coming out of the power supply, because that's the same thing across the resistor. And so I have my voltmeter here set to voltage. And so first thing I do, I adjust this to 1 volt.
You wanna hold this?
Okay, so this is 1 volt. Okay. So here, this will be 0. So measured voltage is 1.009 volts. And then I adjust this one to go to 2 volts. Okay, so this is now 2.122 volts. 2.122 volts. Then I increase this one. Oh wow, it just increased to 4. Okay, hold on, let's see. This is tripping. Okay. 3 point. Okay, you guys will observe some bad power supplies here. Just if this one doesn't work properly, you may want to switch to this one. Let's see if this one is any better. Okay, so increase the current and let's increase the voltage. So we want 3 volts. Okay, this one seems to be worse. Okay, let's go back here. Okay, 3 volts, let's come back here. Okay, 3.3. Okay, hold on. Okay.
It's 4.
Okay, hold on. 3.544 volts. 3.544 volts.
We are going to have 470 resistors.
Yeah, that's why we're actually writing the voltage down, because we use that to calculate the current. So it's gonna be good. Doesn't matter what we have. Okay, 3.96 is close to 4. Then we're going to go to 5, 5.08, 5.08. Then we go down to 6, 6.07. Then we go down to 7. We're gonna 8. 7.39. And one more. Okay, this is cool. 8.24. So after we have done this, we need now to calculate the current. Now we're going to use Ohm's law. Again, Ohm's law tells us that current I is equal to V over R. So what is our R? We measured it. We wrote it down. Okay, I didn't measure this one. Okay, I'm going to turn this off. So we're done with our experiment, right? Turn this power off. Let me turn this guy to resistance. And so we have 325.5 ohms. So I'm going to write it down here. 325.5 ohms. Now, to get my current, I just need to divide. So, anyone's calculator?
Oh, never
Okay.
mind.
So, in this case here, to find the current here, we have 0 milliamps here. Here is going to be the voltage divided by the resistance. So 1.009 divided by 325.58. Okay, so I have 0.00309. So this is the same as 3.09 milliamps. 3.09. Move here. 2.122 divided by the measured resistance 323.58 is going to give me 6.55 milliamps. 6.55. Likewise here, 3.544 divided by the measured resistance is remember the resistance is fixed, 3 to 5.58. This is 10.8 milliamps. Again, this is in milliamps, it's in thousands of an amp. So if you notice here, the 1 milliamp is here, 10 milliamps is there, 100 milliamps is there, 1 amp is right here. So let's go to 3.96. 3.96 divided by 3 to 5.58. So again, this is 12.1, 12.1216 milliamps. And then this one we have 5.08 divided by 325.58. So now we have 15.6 milliamps. Then we have 6.07 divided by 325.58. 18.6 milliamps. Likewise, 7.39 divided by 325.58. Okay, this is now 22.69 milliamps, and so forth and so forth. Right? Guess you guys get the drift. Next step we need to do is to plot this data, right? And again, we have 2 graphs to plot. So if you notice here. Now you're plotting this on your lab report, but for your final report, you need to plot it in Excel. I don't see my plotting. Okay, so it should be right here. I should have some grids there. However, they're not here. But you guys can improvise. So let's start right here. Okay, so on this axis here.
You got a phone call.
Yeah, you can ignore that.
Okay.
Okay, so here we have. Let's start with current and voltage, right? So you can use a ruler, whatever you want to do, just need a simple grid. So on one side we're going to go with voltage, on the other side we're going to go with milliamps. So this is going to be voltage in volts, and this is current in milliamps. Alright? So we start right here and we go back to the data right there. So for 1.09 volts, we're going to get 3.09 milliamps. So for 1.09 volts, we're going to get 3.09 milliamps. Again, I apologize. Probably by the time you're ready to draw a graph, I'll give you some graph paper. Alright? So it's going to be 3.09 milliamps. So you have a point right here. And again, we're going to do the same for the
All up in my spaceship. Yes, you should be scared.
to